Beneath the surface, unveiling hidden realities in concrete materials. The concrete is the backbone of modern infrastructure, but its apparent strength masks a world of hidden vulnerabilities, microcracks, corrosions, and internal damage can compromise structural integrity, jeopardizing safety and tangibility. Uh, the concrete is not a solid block but a material that contains microscopic pores and voids. The distribution and size of these pores can influence concretion's permeability and durability. Excessive porosity can allow moisture to penetrate, leading to issues such as corrosion of reinforcement. Next, microcracks and their formation. Microcracks are tiny features or cracks that occur within the concrete material, often invisible to the naked eye. Despite their small size, microcracks can have a significant impact on the overall strength and durability of concrete, especially to the naked eye. Despite their small size, microcracks can have a significant impact on the overall strength and durability of concrete, especially when they are accumulate or interact with external factors. Understanding their formation and behavior is crucial for ensuring the longevity of concrete structures. Causes of microcrack formation in concrete is like shrinkage during curing type, and there are types of shrinkage like plastic shrinkage and drying shrinkage, and thermal expansion and contraction, load induced stress, alkali silica reaction, the corrosion of reinforcement, freeze thaw cycles, chemical attacks. Impa- and there are many impacts on microcracks on concrete. It reduces the strength and durability. Although individually microcracks may not significantly reduce concrete overall strength, the presence can make the material more susceptibility to, to further damage. Microcracks also provide pathways for water and aggressive chemicals to penetrate deeper into the concrete, excavation and deterioration. Corrosion of reinforcement like microcracks near reinforcement can allow moisture and oxygen to reach the steel, increasing the likelihood of corrosion. The expansion of rust from corroding steel can exacerbate the microcracks and eventually cause larger cracks and spalling. And microcracks are an inherent part of concrete behavior but can lead to long-term durability issues in left unchecked. By understanding their causes and impacts, engineers and construction professionals can design concrete structures that are more resistant to microcrack formation, ensuring better performance and longevity. Corrosions, creeping advance, uh, and a chemical breakdown. Chemical breakdown of concrete, and there are some causes and effects. Concrete is a durable material, but over time it is susceptible to chemical breakdowns that can significantly affects its strength and longevity. These breakdowns often occur beneath the surface and are caused by chemical reactions between concrete and substances in the surrounding environment. And there are some key chemical reactions leading to concrete breakdown like silica reaction. Alkali silica reaction occurs when alkali hydroxides in the cement react with reactive silica in certain aggregates like gravel or sand in the presence of water. This chemical reaction produces a gel like substance that swells when it absorbs water, and its effects like the swelling of the gel puts internal pressure on the concrete, causing cracking and surface deterioration. This can compromise the integrity of concrete structures, especially in roads, pavements, and buildings exposed to moisture. To, to prevent this, use low alkali cement or non-reactive aggregates and ensure proper mix design. Additionally, controlling the moisture content can reduce alkali silica reaction risk. Not only alkali silica reaction, there are like sulfate attack, carbonation, chloride induced corrosion, acid attack, and freeze the damage, hydration of cement, effluents, and etc. In corrosion in iron, the corrosion primarily affects steel reinforcement within concrete due to the presence of chloride ions or oxygen. Iron plays a crucial role in concrete as it is commonly used in the form of steel reinforcement rebar to enhance the tensile strength of concrete. While concrete is strong in compression, it is weak in tension, and steel reinforcement helps to improve the improve this property. However, iron and steel in concrete can also be susceptible to corrosion, which one of the most significant concerns to concrete durability. Consequences of iron corrosion in concrete. Iron, especially steel reinforcement, is crucial to the strength of reinforced concrete. When iron steel reinforcement corrodes, it can lead to serious structural and aesthetic consequences. The deterioration process can compromise the overall integrity and lifespan of concrete structures. Uh, There are some consequences consequences of iron corrosion in concrete like structural weakening, durability issues, aesthetic degradation, increased increased maintenance cost, reduced service life of concrete structures, risk of structural instability and safety hazards, and etc. Next, non-destructive testing methods. The non-destructive testing methods for concrete. Non-destructive testing methods are used to evaluate the condition of concrete structures without causing any damage to them. These methods are particularly useful for assessing the integrity, strength, and durability of concrete without compromising its functionality. NDT techniques are widely used for inspection, maintenance, and quality control of concrete structures such as buildings, bridges, roads, and pavements. Uh, there are some commonly used NDT methods for concrete. Ultrasonic pulse velocity. This methods this method uses high frequency sound waves to assess the quality of concrete. An ultrasonic pulse is sent through the concrete, and then time it takes for the pulse to travel from the sender to the receiver is measured. Next, rebound hammer test. The rebound hammer is a device that measures the surface hardness of concrete. When the hammer is pressed against the concrete surface, it releases a spring loaded mechanism that strikes in the concrete. The distance the hammer rebounds is measured, which correlates to the surface hardness and provides an estimate of the concrete's compressive strength. And next, ground penetrating radar. GPR uses radar waves to scan the concrete structure and detect internal features such as cracks, voids, reinforcement placement, and depth. The radar waves are transmitted into the concrete, and the reflections of these waves are recorded to create an image of the subsurface conditions. Ultrasonic insights, these are already completed. X-ray vision, X-ray, imaging the invisible in concrete. Imaging the invisible in concrete refers to the process of using advanced technologies to visualize and analyze subsurface conditions that are not available or not visible to the naked eye. These technologies help help to detect hidden defects such as cracks, voids, corrosion, or reinforcement issues, which can affect the structural integrity and durability of concrete. Like ground penetrating radar (GPR), it it is it is it is used as electromagnetic waves to probe beneath the surface of concrete and sends high frequency radar pulse into the concrete, and the waves reflect of different materials within the surface like bars, voids, or cracks. These reflected waves are received by the system's sensor and analyzed to create images or profiles of the subsurface features. Mm, Advantages like it provides detailed images of subsurface structures, and it can detect both surface and internal issues in real time, and it is all and it is non-invasive and can cover large areas efficiently. Fiber optics illuminating internal structure. The sensors like fiber optic sensors detect change in strain temperature and pressure within concrete, and it is used to know how much temperature in the concrete, eliminating internal damage in concrete. Like the concrete is a highly durable material, but over time it can develop internal damage that may not be immediately visible on the surface. Detecting these hidden issues such as cracks, voids, corrosion, and delaminations is crucial for maintaining the structural integrity of concrete structures and concrete structures, and various advanced technologies and methods are available for eliminating or revealing internal damage in concrete without causing further harm to the structure. Below are some key techniques for detecting internal damage in concrete, like a GPR, ground penetrating radar. Like it, it is advantages of this is it is non-invasive and fast. It can detect both deep and shallow surface damage, and it provides clear and accurate imaging of internal defects. And next, ultrasonic pulse velocity and infrared thermography and acoustic emission, a X-ray and gamma rays radiography, and etc. Case study, case study, bridge deck deterioration. Bridge Bridge decks are critical components of bridge infrastructure, supporting the weight of traffic and distributing forces across the structure. Over time, exposure to environmental factors, traffic loads, and the material used in construction can lead to the deterioration of bridge decks. Like causes causes of bridge deck deterioration is like corrosion of reinforcement. The most common case of bridge deck deterioration is corrosion of the steel reinforcement rebar within the concrete. This corrosion is typically caused by the ingress of water chloride ions from de-icing salts or seawater and oxygen into the concrete. And next, freeze thaw cycles. In colder climates, repeated freeze thaw cycles can cause moisture trapped in the concrete to freeze and expand. This leads to internal cracking scaling of the concrete. And next, traffic loads and fatigue. Continuous traffic loads, especially heavy trucks and frequent traffic, cause mechanical stresses on the bridge deck, and water infiltration through, through cracks joins faulty drainage systems, and that leads to the breakdown of concrete and accelerates the corrosion to the embedded reinforcement, etc. The strategies for durable concrete. The durable concrete is essential for ensuring the longevity and safety of infrastructure projects. Concrete, while inherently strong, can deteriorate over time due to environmental exposure, mechanical stress, and chemical reactions. However, however, with the right strategies and design approaches, concrete can made concrete can made more resistance to the factors, significantly extending its service life. And ensuring ensuring the durability of concrete involves a combination of appropriate mix, mix design, use of supplementary materials, proper proper curing techniques, and effective reinforcement and corrosion protection. Incorporating these strategies not only extends the service life of the concrete structures but also enhances their resilience against environmental and mechanical stresses. Thank you.